Hi guys, welcome to this Bresenham's algorithm explanation, and this is quite a different approach to go over the math behind this algorithm. It is quite important for us to know that this Bresenham's guy, he invented this algorithm in the 1965, and he came up with this solution like in less than 24 hours. So when you see all of these math sorcery in other explanations or documentation, you think about it and you say, come on, this is not the path this guy took to deduce this algorithm. And it is important to know the year because in the 60s, back then in the 60s, everyone was familiar and related to mathematical optimizations of their code. And the reason why is because they didn't have the hardware and the power of the hardware that you have today. So each line of code that these guys wrote needed to be optimized and needed to be efficient at its peak. Otherwise, their programs wouldn't be able to be handled by the limited CPUs that they had. So universities and companies knew a bunch of mathematical tricks, and they touted to their employees and students, and so they could apply it. And this guy was really familiar with those tricks. So if you're a programmer, which I think you are, and that's why you're here, and I give you the task that for only integer numbers, you code a method or a function that given this equation or that evaluates this equation and just give me the result or tells me if the result is positive or negative. What would you do? And if you thought about a solution like this, a function that takes two integer parameters, which are the values of a and b, and then just evaluate the function, the equation, to get the result, to get its result, you could just apply a Boolean operator and know if it was positive or negative. Of course, your compiler maybe is going to complain about this variable because it is computing a floating point division with an integer. But you can solve that just by doing something like this, float, and I don't know, depending on the programming language, you're gonna have to do a cast operation, like float, something like this, uh, or whatever. So if you are on the 2025, that's okay. But if you were in the 60s, like Bresenham, that was, or this was sacrilege, because this could be avoided. This floating point, this floating division could be avoided. And keeping this practice along the development of the software might result in a slowdown of your program, because floating operations were very slow, and float in the RAM memory was pure gold. So they try to save as much as possible. And how are you gonna get rid of this problem then? How can you get rid of this division? And the trick is very simple. It's a mathematical trick. If you see this equation here, this equation is going to produce a number n, okay, and it can be positive. It could be positive or negative depending on the values of a and b. But remember, we are concerned only in the sign of the result, only if it is positive or negative. So if I multiply this n by any positive number, it will preserve its sign, its previous sign. No matter if it was negative or if it was positive, this multiplication will preserve the sign that n had, because x is always a positive number. So I can leverage this, I can take advantage of it, and I'm gonna make this x is gonna take the value of a, And that allows me to get rid of this floating division, because think about it. If this, let me just get rid of this. Oh my god. Okay, so if this equation produced n by itself, for me to be able to produce n times a, well, I'm gonna have to multiply this equation by a, right? And well, this is going to allow me to get rid of this term, this division, and now my new equation is going to be a squared, a times a, plus b, and it is going to be n times a, which at the very end doesn't matter, because I'm just interested in the sign of the result, which is going to be preserved. And now I have removed this annoying division, and I can write my method or my function this way. Let's call it optimized or improve, and this is going to be int, and I'm not going to evaluate this equation anymore. I'm going to evaluate this one. And now, as this is integer too, I don't have any risk of getting a floating point number, and I can store them in an integer variable. And this has saved RAM memory and CPU usage for our limited hardware of the 60s. And this, my boys, is the trick Bresenham's knew, and the trick he abused of to come up with this solution that does not implement floating point operations or floating point variables to draw a line. So with this in mind, with this trick that now we know, now we can start to create this algorithm from scratch. So let me drive you through another concept that is going to simplify our math even more. And this is very simple. Let's think about this matrix of cells, or this 2D plane as our monitor, as a matrix of pixels. And of course, we can only have whole components for coordinates of our pixels. You cannot have like 7.5 as x and 5.1 as y for a coordinate of pixel. No, pixels are whole units. You can paint them, or you can turn them up completely, or just not. So this plane here is gonna have only whole coordinates, but it's very simple what I'm going to show you. If you already read this function here, you're going to notice that it's just representing or painting this line on our matrix of pixels. It starts in the origin, and then it starts to increase the x component to draw an horizontal line. And if I copy this line, which is the same exact line, but I want to paint it now, if I want to paint it, I don't know, here, for example, what would you do? What would you do to take any line that crosses the origin, or that starts at the origin, and do something like this and move it to any other position on our screen? Well, we can use offsets, and this method here is going to help us to achieve this translated line, which is going to be the same previous line, but moved by an offset in x and an offset in y. So what you do is just take the x offset and add it to each one of the x components of the coordinates, and that's going to move each one of our pixels x offset units to the right in this case. And the same thing is going to happen with the y component. You're adding an offset of 7, so they will not only be moved to the right, but also upwards, giving us this translated line, which is this same line but just translated, just by using offsets. And why is this relevant for our algorithm? This is going to simplify our math a lot, because no matter which line you draw in the origin, you can just use an offset, any offset, to move it wherever you want it. And this is a key concept that you can not only apply in code, because this is the code side of the solution or of our analysis, but you can also apply it to math. Okay, so now we're going to connect this to simplify our math. Here we have a 2D plane, but this is a normal mathematical Cartesian plane, however it is called. But this one, you can use floating point coordinates. All of these space between the edges of the lines are floating point points. Any random point that you put here is gonna have a floating point pair of components to represent its coordinate. So now we're going to connect with the previous concept, the math with our previous concept. And for that, let's just welcome to our famous line equation. And this y equals mx is just a way to compute points given an x value and a constant slope. And I'm not going to go over the derivation of this formula or the explanation of the concept of slope. Maybe in a different video. I'm going to do a different video for that, and Pythagoras and everything, but I'm going to assume you guys are familiar with this. And many of you may know it as this equation, or plus z, or something like that, but guess what? We don't need it. Why? Well, the reason I just explained it before. So let's just compute this line. Let me just pause the video and compute. I'm going to give you an example. Let's say we're going to compute the line with 1/5 x. This is my slope. The slope is going to be 1/5, and I'm going to compute it. And here you have it. So after computing these 5 x values in our equation, I was able to draw this line. And if you pay attention to what's going on with the equation, it's just that we are multiplying the slope x value times. So for the first value, which is 0, the first value I computed for x, 0 times the slope is going to give us 0. That's why our line crosses the origin. But for the second point, which is x1, this coordinate here, if I try to get the corresponding y value, it's going to be 1 times the slope. And for this value, it is going to be 2 times the slope, and then 3 times the slope, and then 4 times the slope. So our slope is practically all what matters when we are drawing lines that crosses the origin. And this is important because that means that if I increase the slope, let's see, for example, if I make the slope a bit higher than 1/5, my line is going to be above this one. And if I make it higher and higher, I will be able to draw any line in this quadrant. And even in any quadrant, if the slope is negative, or, well, we combine the coordinates. But let's now focus on this quadrant. And you can see that depending on the slope, we're going to advance faster or slower in the y-axis. And, well, now what we're missing is, okay, and can we do with math the same that we did before with code? Like taking this line and moving it upwards? Because you already showed us that we can represent any line just with changing the slope. We can compute any line, but can we translate it? Can we just do something else than increasing like its angle here? Of course. And let's, for example, shift or move upwards this current line that we have here. How would you do that? Well, think about it. Just I would have to take each point and move it or translate it upwards. So this y would be any offset above, and each point would be above by the same offset. So that means that if this produces my y's, my y values, which are these ones, and I want higher y values, I could just add an offset here, like a b or z or whatever you want. So let's say, for example, I want to move or translate this line upwards for 3 units, and if I add a 3 to the equation, to the right side of the equation, I'm gonna get for 0, instead of 0 I'm gonna get 3, because this is going to give me 0, and now my offset is going to produce this plus 3, and our point is going to be moved here. And the same for this point is going to be moved 3 units upwards, and the same for all of the points, and at the end we're going to produce the same line, but translated upwards in the y direction, you know. So that's the vertical translation. And now how would we get the side, I mean right or left translation? So let's say I have some copied lines here. They are the same. So now you can see that they are the same, but now I want to get, for example, this line. I want to translate it 4 units to the right. How can I do that? And if you notice something, is that the y value we got in 0, we need to get it in 4, in x4. I mean, if I input 0 for this line, I got 0. I was getting a 0, but now I need to get that 0 here in 4, and the value I was getting in 1, now I need to get it in 5, because I have shift to the right all of my x values. So if when I input 4 I need the value 0, I just need to subtract my offset here, and that is going to shift all of the points. So if you put like 5 in the x, you're gonna get a 1 times the slope, which is the value you had here, and now you have it in 5, in the 5x value. And the same for the 4. If you test with the 4, you're gonna get 0, and now you're gonna move this value here. But this is like the same of translating it vertically at the very end, because this is just another constant, because slope is constant and this is constant, so that is always going to be subtracting the same amount. But we don't really care about this, and the reason why is because let's say we have a shift of 4 units to the right in a shift of 6 units upwards, and we would have this line here. But we don't need to do this math because we have code. If I want to put pixel or light pixel, I'm just gonna have to take the current x value, computed x value, and add this offset plus 4, and to the y coordinate I would have to add just a 6, and I would just have to store these offsets in any variables, so we don't have to care about these constants, these translations. We only have to care about this form of the line, because then we can move with coding any point to wherever we want with the offsets. And please don't get confused by this positive offset, because we did it with a negative in the math, but that was because in the equation we needed to go back in X to retrieve a Y output that was produced by a previous X value. And same for 5, we needed to go back to a previous X value to retrieve it, and so that way we could shift this line to the right. So just so you know that this in code doesn't work like that, because in your monitor if you have a pixel or a set of pixels and you want to move them to the right, you just add a positive value, so they will move to the right in our monitor space coordinates. And if you need to move them to the left, or an entire set of pixels move to the left, you just need to subtract. So this is more intuitive in the code sometimes than in the math. But with this in mind, we are ready to visualize the way our algorithm is going to work, and then jump into the math without worrying about these constant terms that at a long term in our derivation process, they will just turn into terms canceling processes that just come out of nowhere. So now let's get back our screen space, because we're going to take this line and we're going to represent it in only whole coordinates. And remember, we can plot only whole coordinates pixels in this screen space, and we're going to do it just with our sight, just with our own eyes. And what are we going to do? How are we going to start? Well, we know the first point is the origin. Just by the form of the equation, we know that if I put a 0 to x, then this is going to produce 0 for y. So my first step is always light up the origin pixel, and that's it. But when I move on, when I advance on x, I'm going to get to this point, which is something like 0.2, and well, I don't have a 0.2 y coordinate here, but this is much closer to 0 than to the next pixel. I mean, it's closer to this 0 than to 1. Just look at it. Look at this. The distance is closer from the previous or the current y value. So I'm not going to increment for this pixel in y. I'm just going to increment it in x. So let's just light it up. Okay, easy one. But notice that as soon as I get closer to the half point of this distance, that we have here, it's harder for me to determine if the points are above or below or are closer to the next y value or the previous one or the current one. I'm sorry. So what is it going to be? What is this source of truth going to be? And it is simple. It is just going to be a middle line, a point that breaks that distance in two halves. So if the current point is below, I'm just going to keep my y value. But if the current point has overpassed this half y value, then I'm closer to the next y value, and that's what is going to help me to decide. So for this value 2, let me just keep computing. For this value 2, I'm still below it, so I'm going to go like, I don't know. I know it's just 2/5, but it is still below the line. And this one is over the line, so I am now closer in this point to the next y than the current y that I've been using. So now this 3 coordinate for x is going to pair with the next y because has overpassed the middle point. And now Now that we overpassed that point, there's no sense to keep testing against this line. Now I am concerned, so all of these points have been rounded to here, but now this has been rounded to here, and this one, or all of the next ones, are always going to be above this line. So my next decision is if I keep this y value or if I increase it to the next. So the line I am concerned of now is this one. Let's paint it in red. It is going to be this one, which is nothing more than adding 1 unit to this, because I'm moving it 1 unit up. So that is going to be 3/2, and so on and so on. Then I'm going to check against 5/2, and that's going to make my decision of keeping my current y value, or at any point increase it. And that way I'm going to give the impression I'm making a line by lighting up pixels. But now, how are we going to translate this to math or code? And especially, how are we going to do it without using floating point numbers? And the answer to that question starts by putting ourselves in the next situation. So let's say I give you the task of drawing the corresponding line for a given equation with a constant slope. And if you're not allowed to use a calculator, just pencil and paper and yourself, maybe you would come up with something like this. The process of computing our points and the process of using those points to draw your line. But let's say that you want it to be really accurate and you computed 6 points. But when you get to the 4th point in your drawing, you notice that there's kind of a change of direction. And if you're not a politician or something like that, you would probably think like, okay, I messed up on this point computation. So how would you check, or how would you correct your point values? So if you remember, this y is produced by multiplying the slope these x times. So if you do it again and you get the right value, if you compare them, well, there are 2 options. They're different when you are mistaken, or they're equal if my point belongs to my line. So I can use this, because if they are equal, and my point is on my line, it should fulfill that this subtraction is going to give us 0, because I will be correct. But if not, like in this case, that my y seems to be bigger than what it should be, what do you think this equation or this operation is going to give us? It is not going to give us a 0. This is going to give us a positive number, because the y value is exceeding what its real value should be in our line, or this point is above my line. It doesn't belong to this, and this operation is telling it, is confirming that. But if you want to make sure that all of your points are correct, then you would just do your computation again, like this, and all of these subtractions should give a 0 as a result. All of them should give you a 0. And let's keep the testing for this point, and now you get the idea. But seems like this one is positive, so it means that this point is above my line. But what if the situation was the opposite, that the point is not above, but it lies below than where it should be? So If the y, for example, if the y is less than what it should be, then this is not going to be positive. This is going to produce a negative result. And that is a huge tool that we can use to know if a given point, because all of these are points, and we are practically evaluating in a subtraction of this form. Let me just write it here. In a subtraction of this form. So this is going to help us to evaluate a point and know if the x value of my point really produces the y one, because if it does, this will give us a 0 as a result. But if I have a wrong point or a point above my line, it is going to be positive, the result. And if this point is below the line, it is going to be negative. And that's exactly what I'm doing here. Notice that this is just replacing the x here and the y here. And it is giving me, in this case, a positive number, and in this case it would give me a negative. And in the other points, which are correct, this is going to give us a 0. And this is very valuable information, because remember that our monitor has only whole coordinates. We don't have floating point coordinates. So that's the reason why we had to decide over these line points if we approximate them to the current whole y value or the next one, because that is practically the pixel coordinate that we will light up in our monitor. And we did this decision with our sight, with our own eyes. But now this formula, if for any given line with a constant slope, it tells me if a point is above or below, now I can know if my line at any given x coordinate or at any given point has overpassed the current limit to decide over the y value. And this is, in this case, the first point of evaluation is the half. So in this case, if this point evaluates in this function as a positive, which means it is above the line, that means that my line has not overpassed the half. So it is closer to the current or the last y value I used than the next one. And again, if I apply this to the next point, whenever the x is incremented, then I'm going to get in this case, a positive again. So I should not increase y, I should still plot it in the current or the last whole y value. But look what happens here. For this specific line, this point now is going to evaluate to negative because it is now above, below the line. So my line has overpassed that point, and that means that for this x value, I should increase by 1 to the or I should increase my y value to the next whole y value, which in other words is of course increased by 1, and so on. So now that I am here, my decision lies on this reference. I'm no longer going to evaluate to this one because I already passed over this line. So now I'm going to increase my evaluation point by 1, and now I'm going to decide if I should stay in this y value or at any point after evaluating this point, after evaluating this point, or these, or these, or these, and so on. Whenever this equation evaluates to negative again, now I'm gonna have to move from this to this y value. And again, I increase my reference half, and that is going to apply to any line with a slope less than 1. I'm going to explain this later, but just let's focus on this quadrant because that's how the Bresenham's algorithm base works, and then we're going to make it work to any quadrant. It's just playing around with the order of the variables. But yeah, with this in mind, let's just jump into deducing our math from this equation. Let's deduce the entire algorithm with it. And after cleaning our screen, we have our main character, which is this equation, but now we're going to use this form of this equation, which is going to tell us if a given point, or help us to evaluate any point to know if it is above or below, and do the process we just explained before. But I told you that this was going to be focused, well, this algorithm was going to be focused on this section of this quadrant. And if this is the Cartesian plane, then we would be applying this logic to only this section of this quadrant. The reason why is because the testing process that we are doing is against reference points that grow vertically. And look at this line, for example. Look at this one slope line. Every time I increase in x by 1, I increase in y by 1. So that means that I'm not going to be able to jump into the next y value if I have not previously jumped into the next x value. That's what this slope mean. So what's going to happen with all of the lines below it? Well, they're going to have the same behavior, and some of them are not going to be able to jump into the next y value before increasing x by multiple times. Like in this example, look at this. Before increasing y from here to here, we had to make 1, 2, 3, 5 steps, right? So that's why we can safely iterate our x component and asking on each one of those steps if we should increase y or not. But that's something that is not going to happen with the lines with a slope bigger than 1, because look at this line, for example. My first, let's remove this one. My first equation or decision point would lie here if I apply the same logic to these lines with a slope bigger than 1. And it would tell me, okay, you're gonna have to light up the next y value. So I would increase from 0 to 1 in y. But in reality, this line should have increased 5 units. So this logic that we have for this section of the quadrant is not going to apply here with the x as the increasing step and the y as being the one that is evaluated if has to be increased or not. So it's very simple. What we have to do is just do the same, but swapping our coordinates decisions. So now y will be always increased, but x is gonna be the center of our decision, because we know that now in order to increase in x, I would have first to increase in y, because y is the one that now has the lead. It increases faster than x. So okay, no more circles, no more to explain about details. We have our equation here to evaluate any line with a slope less or equal 1. What's gonna happen? I'm going to evaluate to any of these lines, for any of those lines, after plotting the origin pixel. I'm going to evaluate this point here, and that is going to be no more than a half for all of the lines. Always the first point is going to be 1x, a half in y, because that is my first rule, my first limit. And this is going to be evaluated here, which is going to be this, okay? And in this case, this evaluate to positive. I'm only concerned about the sign. And then I'm going to increase x, but not y, because I'm still below the limit, the half limit. And I'm going to get this. So look that x will be always increased by 1. And in this case, this still gives me positive. And in the next one, I'm gonna have this 3 times the slope. In this case, it is negative because this point that I'm evaluating, 3 comma a half, is below our line. So this is going to be negative. So now I'm gonna have to increase y, but also I will start to evaluate in higher y point, higher by 1. And that means my next evaluation is going to be this one, and in this case positive, and so on. So if you notice, if I keep increasing y at any point, it is always going to have a division. And remember that Bresenham was this algorithm was invented in the 60s era of programming, and this cannot be handled by a CPU. I mean, it could. I'm just exaggerating, but this could be improved, and we saw how at the very beginning of the video. So I've noticed that all of my evaluations, all of them are going to have a division by 2 in this term of the equation, in this side of the equation. So as I am only concerned about the sign of the result, I can do this. I can multiply all of this by 2, so I can get rid of the division, and I'm still going to get the same sign, the positive, just doubled. And if it was negative, it will be negative, but just doubled. So if I'm going to do this for all of my evaluations, well, this I can just summarize as giving a different shape to this equation. I can multiply by 2, and whatever sign these results is going to be the same sign, just multiplied by 2. So my equation has transformed into this new equation. Just let it there, leave it there, and now let's give it the new form. 2 times y minus 2mx, which is the same, which is the result of duplicating the entire equation. And this is the first transformation of our equation. So now if I evaluate the first point on it, I'm gonna have 1 minus twice the slope for this first point, and it's going to be positive. And if I evaluate the next point, then it's going to be 1 minus 4 times the slope, and for the third one it's going to be y minus 6 times the slope, which is going to be negative, because at the end any x I'm just multiplying it by 2. So this is why I have an increase ratio of 2 2, 4, 6, and if we keep going, this is going to be 8, 10, and so on. But as this one gives us a negative, the next one is going to be 3 over 2. So this is going to be 3 minus 8m, and so on. But this will preserve the right sign of this evaluation. And that's it. But many of you would say, okay, but m, as far as I know, is the result of a division too, which is delta y or over delta x. But remember, as all of our equations start by the origin, I can just take any point and divide it by x, but it's still a division. So I'm gonna write this equation again, because this is equals m, our slope. So this equation is going to look like this now: delta y over delta x times x. And this is going to be my evaluator equation. It's the same, but we can apply the same trick, and that is why I told you that Bresenham abused this trick, because now he has a delta x, and this is going to give us a positive or a negative or 0, but no matter what is the result, I'm concerned about the sign, and if I multiply by any positive number, I will just preserve the sign, or the 0 in case it is 0. Any number multiplied by 0 is 0, and any positive number multiplied by any positive amount is positive, and so on. But if I abuse this trick, multiplying the entire equation by delta x, I'm gonna get this form now: twice delta x y minus twice delta y times x. Okay, and don't get lost by this change of forms. We have just applied the same trick twice, of multiplying the entire equation by a positive number, just to get rid of the divisions having the same sign as a result for any evaluation. But we're just evaluating a point, and this should give us positive or negative or 0. And so let's do that. Let's evaluate. And now let's evaluate again. Do the same evaluation again, and now this will look like y. I'm going to replace it here, so it's a half, so it will cancel with this, and it will just give us delta x. Okay, and this is going to be a 1, and this one is just going to be a 1, and so this means this will be our first evaluation. In this case, just for this line, is going to give us a positive. But let's analyze again this. Now that I know that for the next iteration or the next evaluation, as this is in code going to be a for loop or a while that will be iterating over the x value, you know that the next s value is going to multiply all of these by 2. So we're gonna get delta x again minus 4 delta y, and we're gonna have here forget about this side of the equation. We're always going to increase. For the next one, this is going to be 6 delta y, and this is going to be minus 8 delta y, and so on. So in each iteration, I can just take the first evaluation value that I got and subtract from it twice delta y, because this is going to be this same number, this same result, but minus 2 delta y. And this is going to be that same previous result, but minus 2 delta y. So you just keep subtracting minus 2 delta y to the previous iteration result. And whenever this gets increased, look at what's going to happen. In this case it is 1, but whenever this gets increased, it is going to advance by 2. So for the next, let's say here, I don't know, I'm not sure, but well, whenever it is going to take this or these, right, and so on, is going to result in 2 delta x more than the previous result. So this is going to define the behavior of our iterations. So with this in mind, let's just write code based on this, because these are going to be the evaluations on each one of the iterations. Here we have our coding area, and let's assume our method is going to get 2 coordinates. I know you can use point or whatever class you can use in your programming language, but let's say we're gonna have 2 pair of coordinates, which represents each one of them represents a point. And let's assume x1 is always going to be bigger than x0, and y1 is always going to be bigger than y0. So just the happy path for our base code. Because, well, whenever you want to draw a line, you just provide 2 pixel coordinates. And remember that the heart of our code is going to be this evaluation here. And notice that we have these terms all the way down in our evaluations. So we're going to start by getting those terms. In the x is going to be x1 minus x0, and in the y it's going to be y1 minus y0. So now that we have these, remember that all of our lines, we explained them as if they were going to be painted in the origin. So I'm going to start in the origin. Int I is going to be 0, and int j is going to be 0, but I is nothing else than just the current x value, and j is nothing else than the current y value, and we start at the origin, so both of them are going to be 0. Okay, and if we're going to start at the origin, and our lines are going to have a slope that fulfills this condition, then our point, or our first point of evaluation, is always going to be this one that we have here. And replacing or evaluating this on our evaluation formula, we're going to get these always for any pair of points. We're going to have to evaluate the first iteration against this. So I'm just going to create that first value, which is the x minus twice delta y. Okay, now that we have our first evaluation value, I'm going to start to iterate from I to the x. And I know many of you would think like, okay, but why don't just x0 x1 and increasing x0 one by one? It's because I'm just adjusting our algorithm to all of the logic that our lines are going to start at the origin. So think about it. If we just start at the origin and I have, let's say, these 2 points, our delta x is going to be shifted here, and we're going to iterate from 0 to here because we're going to move this line to the origin, to start at the origin. And now what's going to happen? Well, first we need to put our pixel. We need to light up pixel with the current I and j values and the color, whatever it is, because we're start at the origin. And now I know for sure that at the end of this iteration I'm gonna have to increase I or x by 1. So I'm going to do this, increase I. But remember that with increasing I, our next evaluation is going to add this negative term to the current value. So if this is my current iteration, which is this, and I'm always going to increase x, look that when I increase x, is nothing more than just add these to the value. So I'm always going to add this term. A is going to be, or subtract twice dy, because that's going to happen for all of the iterations, always subtracting twice delta y to get the next evaluation value. And now we have solved the x increment, but remember that our decision on y is going to depend, I mean, the next pixel, if I keep my j in the same value or if I increase it, is going to depend on the value of the current evaluation. If the current value of a is less than 0, right? I'm not saying anything else than if evaluating this point is below my line, which is in this case is not, but for example this line it would be, but whenever this is less than 0, that means that my line is above, in the next iteration needs to increase its y value, because it will be closer to the next y than to the current one. And if I increase y, remember that I also have to, for the next iteration, increase the reference middle point, which is going to be reflected here. And we explained the math previously, that it is going to take this double increment, like twice delta x and plus twice delta x plus twice delta x, and so on, whenever the y increases. Not always as the x. Look that the x is always increasing, but whenever the y increases, whenever I round up to the next y value, now my evaluation term is going to get increased by twice delta x. So if y is increased, then a is going to be increased by twice dx. And here, guys, here you have the Bresenham's algorithm implementation, but for a line that lies on the origin, I mean that starts at the origin. So how can I move it back? Remember, we can just add an offset to each one of the pixels, which is nothing than this. is just adding the first point to all of them. So if I take this point to the origin, how do I move it back there? Well, this pixel, I would have to add 2 vertically and 2 horizontally, which is nothing more than the original first point. And so on, I would have to add to the other points, all of the remaining points, and all of them will be shifted back to their intended position. And you would say like, okay, but this is redundant. Yes, of course, I made it. This is redundant in the code, so I didn't have to go over a complicated math. We deduce these terms without canceling with processes or something like that. No, just a very consistent process of deduction. No terms cancellations, weird assumptions of this is constant or whatever. No. So this is why I can play redundancies in the code, with redundancies in the code. But this can be written in a better, now that we know this, we can just check the code and write it in a better way. And so we don't have to do this addition all of the time. So I was going to start at x0 and j is going to start at y0. But if I start at x0, now this is something that I can do, and these guys should work. I know this can be improved, but that is not the focus of this video. You can just do whatever you want to make it look better, but I wanted to focus on the math and how do you get to this term in specific, in how these additions of constant values like twice delta x and twice negative delta y and twice positive delta x can help us to optimize our algorithms for drawing lines in such a way that we don't need floating points. And a little mistake here. Okay, and here you have it. So yeah, this is it for the basic implementation of it. Now let's just code this. I'm going to use Z++ in a really simple window made by Chili, which is a wrapper of the DirectX 11 framework, I think. But just to get pixel access and a basic window to draw any line. And so let's jump into it, and then we're going to go over all of the cases where we need to swap variables and make this work to any other section of our Cartesian plane. Okay, so here you have it. This is an implementation in C++. This is just a wrapper for DirectX 11, the Chili framework. I would recommend you his channel in order to understand C++ basics and game development. But today we're going to use these just to draw a window in the screen and have access to the pixels. And so here you have the implementation of this algorithm, and we're going to test it. I'm going to just use it, Bresenham's line, and I'm going to provide my first point, and I'm going to advance 100 pixels to the right and 50 pixels upwards. And I'm just going to provide a color for this line to be rendered. And here you have it. This is our line, and if you don't believe it, let's just decrease the slope just a bit. And let's build this again. And there you have a new line, and let's give it a horizontal slope. And there we are. But let's keep decreasing this slope. Let's see what happens. What if now my second y is below my first one? Let's just give these 180, which is 20 pixels below this y point. And let's just put a pixel to reference that specific point. Let me just take this piece of code, replace it here, and give it a yellow. And now we should be touching that point. But look, that the minimum slope we can draw is 0, and we're not able to draw negative slopes. And if I comment this part of the code to see what happens with this line, and now you're going to see that it just draws the minimal slope line possible, which in this case is 0, a slope of 0. And why is that? Well, it's very simple. It's because our algorithm is always prepared to overpass this point, this line. But when you have a negative slope, what the line does is going downwards, so it is never going to overpass this reference line here, because it is always decreasing. So how can we do this? I mean, how can we fix it? And remember that our Cartesian plane is something like this, and now we're able, with this logic, we are able to draw lines only in this section, because our logic was made for this section of the Cartesian plane. And as the monitor coordinates are inverted, that's why in the monitor we are able only to draw our lines in this specific section of the Cartesian plane. So what can we do to fix it? Well, it's very simple. If you check this image, it's the same process, only that this time we're going to be decreasing y. And now we're going to have this, and we're going to have to test our line against this. And if that is the case, now that means that my decision is not going to be about incrementing y or keeping its current value, increment it or keep it, but decreasing it or keep it. And that means that my first point is not going to be this. The first point I'm going to test my line against or the first point I'm going to test in this evaluation equation is going to be the negative, just to check if this line already overpassed, or I don't know, already went below this point. So how are we going to do that? So if this is my first point for all of the lines with negative slope, then this term here, which is our first evaluation point, or the result of that evaluation, then that means that this is going to be negative. And whenever I increase it, I'm just going to have negative all of these components of my evaluations, because we are decreasing on y. So this y is always going to be negative, but the magnitude increasing reason is always going to be the same, by 2, but downwards, I mean negative. So I'm just going to say that my first point is negative. And you would say, okay, and why is this one not inversed? Well, we're still advancing the same direction in x-axis. So this is not going to change. My x is going to be positive. And also, you may say like, okay, but if this is always negative and this is negative, then I'm always going to evaluate to negative. And I will be always below the line. But no, because now as our y y1 is is minor than the y0, this term, or this delta y, is negative, turning all of these in positive. So it's the same. It's practically the same logic. It's like when we were evaluating our computed points, we're gonna have in this case pure negative y values. y1, y2, y3. X is going to be positive, x1, x2. But when I do my subtraction, I'm going to subtract against a negative slope, right? Because now our slope is negative. So this will keep the same behavior. This is a general formula, no matter the sign. So it's just a clarification, because sometimes we see details in the explanation and we wonder things about it, but that's okay. It's better for us to try to go over all of the possible thoughts that you may have about it. And now where were we? So yes, now we're going to test against this first point. This is going to be negative dx. The right part is going to be the same, but now we are concerned about decreasing, and we said this was going to be negative always. So now we add negative delta x components duplicated on each iteration. But now look at this condition here, and this condition is asking if the evaluated point is less than 0, and that's going to work here because we are advancing upwards. So once the evaluated point is below us, we increase. But in this case, I'm concerned not if I'm already above, but if I'm already below. So I'm gonna have to change this condition to the opposite. It's going to be bigger than. And with this, we have the implementation that will allow us to draw on this part of the Cartesian plane in our monitor. So let's check that for this new version of the algorithm, or a new component of the algorithm in general. And here you have it. This is the new implementation for this specific section of the Cartesian plane. And let's just draw our lines. But now let's draw this one with negative slope, with this method that we just created. And now we can see that we can draw on this side of the circle, or the Cartesian plane. And if I change this to yellow and I keep increasing or decreasing to 150, and let's say like 100, then we're going to be able to draw our lines on all of these points. I don't know why is this one larger than this one, and the reason why, I guess, is because I didn't do a 300 version of it. 250, 200, whatever. So let's just do this one, but with a slope of 300, if I'm not wrong. Let's build it. And now you can see that we can draw on all of these part. Now let's attack this side of the Cartesian plane, these sections. I'm going to attack them because it's much easier to do it first. Look, if I want to draw a line in this part of the Cartesian plane, it would look something like this. But if you notice, this is the same as drawing it here. So what I can do is just swapping my x values, because when we have a line in this part of the Cartesian plane is because in my second x value, like my second point, the x value of the second point is less. That's what we're trying to say, but in code that doesn't make any difference, because it's just the same line or set of lines that I can draw here, and the same for these ones. The lines that I draw from here to here, these are practically the same that I can draw here, just by swapping the x values. Well, not only the x values, but swapping the points. I'm not going to draw a line from here to here, because I'm not going to do a version of the algorithm for this. No, I'm just going to swap the points when they come into my method. So I'm just going to, if you give me this point first and this one first, that means my line is going to go into this direction, into this one. Yeah, look at it. Right? Is in this direction. But I already have the algorithm that draw the same line, but in this direction. And as our line doesn't have a direction like a vector, there will not be any problem. And the change will be reflected here. It's just in case my first point x is bigger than the second point x, then I'm just going to swap the points. So I will be able to reuse the algorithm to draw them. And this, now we can test it just by swapping some lines here. Or let me just take the same original point. Look that we are trying to make kind of a circle, all of the Cartesian plane. So if I put these as the second point, but now I want to go, for example, to 100 units to the left in the x-axis, but I'm gonna put it here, 100 units from the same starting point. So I'm going backwards in x. Look, this value is less than this one, and I'm going to go, let's say, also backwards on x. Let's go for 150, and let's give it a different color. Let's see what colors we can use. Let's go for a green. And if I go here, look, I can have now I will be able to do the same. And let me just complete it. And here you have it. We are using the same two methods for negative or positive slope, but now with this validation that we added, that we can cover now this portion of the Cartesian plane. And now we're just missing the positive slopes. I'm sorry, the slopes bigger than 1, which are going to be the most vertical lines. These we can call it like horizontal lines, and these ones in these sections of the quadrants, they will be called the vertical lines. Okay, so how can we get that working too? And I'm going to be very simple on how to fix this for these sections of our Cartesian plane, because if you notice, the same thing that, or the same logic that we applied, that we applied to this situation right here, this same logic, oh my god, this same logic, it's at the end is going to be the same that happens here. Let's think about it as if we rotate this and now our y-axis becomes our horizontal axis. So if I rotate the circle, this would be y, and this would be negative x and x. So it's just a matter of applying the same logic in the same math, but now y will be x and x will be y. Because think about it, I mean, for this specific case, when the slope is bigger than 1, and now I will always advance on y by 1 unit before getting to advance in x by 1 unit for all of the possible slopes above 1. So that means that my equation, my base equation, would kind of change. It is going to be something like this. X is going to be equals mx, my. But as now we are advancing vertically on the x-axis, so my definition of slope will be the inverse. Is no longer going to be this one, but this one is going to be how much I advance on x when I advance certain amount on y. And if we apply all of the same process, we're going to get to the same formula but inversed. So now we're going to evaluate x minus my will be our evaluation formula, which would turn into this is going to be double minus twice my. Do you remember that we did that because of the middle point was always divided by 2? And now if I rewrite this as delta x over delta y by, or multiplied by y, I'm going to get to this form, because if this is my evaluation formula, I can play again and apply the same Bresenham trick. Well, this is not his trick, but the same mathematical trick. And I'm going to get to this. Twice delta y by x minus twice delta x by y. And this would make that, let me just move it here, and now take a look that the terms have been practically swapped. Now this is the positive, this is the negative, and if I take the first point of evaluation for this form of the formula, now these would always be evaluating to a half or 3 halves on the x, right? Because our limits, these lines here now are going to be in the x-axis to do the evaluation if our line already overpassed them. So this is the term that is going to look something like delta y, and if increased, then it's going to be 3 delta y and then 5 delta y if increased in every iteration. But now is going to be this component, the one that will constantly increase, because y is now our rule axis, and this would be something like just minus twice delta x minus 4 delta x and minus 6 delta x and so on. And this one is the one that we are going to decide if we increase or not, but this will always be increasing because it's now multiplied by a y. So my first point is now this one, delta y minus twice delta x. And if you continue doing the analysis, you're just going to be applying the same logic, the same algorithm, but all of the x and y's are going to be interchanging. Now I will have to add, instead of dx, I'm going to have dy, and in this case, instead of dy, I'm going to increase dx, and instead of increasing x every time, I'm going to be increasing y, which in this case will be j. And yeah, so let's just finish our video implementing or just using the implementations we already did, but now let's apply them to an interchanged axis version of them, so we can draw lines in any section of our Cartesian plane and of our monitor. And as I told you, let's just use our previous versions of the algorithm, and now let's just make these y0, y1. Look that now we are trying to do the same as I told you, as if we had rotated our coordinates, right? So let's apply this evaluation here, this condition here, to be based on y. And now I am not going to use this initial term, but this one. So this is going to be dy, and this is going to be dx. And I'm just going to show you the way I do it in this part of the algorithm, and then I'm just going to skip the video completing this version. So at the end we will be able to draw lines in any direction. So we are here, and this j, this is now going to be j before it gets to y1, because it starts in y0, and this is not going to be j but I. And let me just check this term. So in this case, let me just, it should be dy, this should be dx, and this should be j, which is the one that will be increasing every iteration. Now it's y, the one that is increasing every iteration. In our terms, look that in case we enter to this condition that we overpass the limit, now we are adding dy's, and we will keep adding on every iteration a dx or negative dx, delta x, which is the opposite here. And okay, let's just pause the video. And finally, here we have our bigger than one slope version for drawing a line, which is just this same algorithm, but with our variables swapped, dx and dy, and y and x in all of the logic. And now we are going to go over the negative slope version, and again we have just swapped the logic for dx and dy, and this condition based on y instead of x, and increasing j every time instead of I. and so on. And here I have a method ready to unify all of these components of our Bresenham's algorithm, which is much better. I also rendered this square with all of our 4 algorithms, or all of our 4 methods, to be able to visualize that it works. So how are we going to do this of unifying? Because it's very simple. It's just this is no longer about deducing analyses or whatever. It's just watch the code and unify our algorithms. So something that I want you to notice is this, our first implementation, matches with the logic of this one. They do the same condition. If they check this condition, where both of them share that condition, and also big part of the code if you pay attention. So we can just unify this, because it starts to change here. So I'm no longer going to have this version. I'm just going to move this code here, and that would be one method which will be in charge of drawing horizontal lines. This and this one will draw horizontal lines. And so let's just do that. I'm just going to take this. I'm just going let me just pause the video, or not, let me just put it here. So in case, I mean, if this was for a positive slope, not negative, and in this case we would just have to check if y1 is bigger or equal than y0. Okay, else I'm going to have this. Okay, so now basic Bresenham's line is going to help us, or is going to draw all of the horizontal lines. And now we can just get rid of this one here, this method. And now we have basic Bresenham's line. I'm going to rename it to horizontal, or draw horizontal line. And also let me just go to where it was implemented and remove this. And now wherever I had it, wherever I had this implementation, I'm just going to replace it. Okay, so now we should have the same behavior if we check our square. That's great. Now let's go back and unify our vertical versions, which are these two. And here you can see that they share the same code until this point, right? If I just do this and do this, they share the same code, and they just differ starting here. So I'm going to do the same. I'm going to take this, but now remember, in this case our condition is based on x. If it is a positive or positive horizontal slope, we're going to apply this algorithm, else we're going to apply this logic here. So now we can just get rid of this, and when this starts to complain, and now we can rename these to draw vertical line, and let's change the name again here, and let's make sure everything is okay. Okay, if this is positive, I think it's okay. So what was the name? Draw vertical line. Okay, now draw vertical line and draw vertical line, if I'm not wrong. And here you have it. So what's left? Notice that now I have two versions, and I just need to determine when am I gonna have to draw an horizontal or when am I gonna have to draw a vertical line. And that, of course, is based on, let me just check graphics. In the final method, I'm going to name it drawLine 2 because I already had all of this implementation. I already had it before making the video, so I already had a drawLine method. So now we are going to check if, or we're going to check what makes our slope bigger than 1. And when our slope is bigger than 1, it fulfills that y1 minus y0, the absolute value, is bigger than x1 minus x0 absolute value. And if this is the case, then I'm going to execute draw a vertical line, which I'm going to vertical line, and I'm going to give it x0, y0, x1, y1, and the same color. And if not, I'm just going to draw a horizontal line. Draw a horizontal line. And now we're able to completely replace this and this for our new method. And here you have it. So finally, this is the end of the video. We have our method drawLine. Yes, it was, I don't know if it was more than an hour. I guess it was. But come on, most of the video was going over other concepts that would help you to intuitively understand the Bresenham's algorithm. And if you didn't understand, maybe you just learned a pair of tricks along the way. So yeah, this is it, guys. I'm sorry, I'm not an experienced YouTuber or teacher or whatever. It's just I would say my first video. Also, English is not my native language, so sorry whenever I struggled with some words or terms when speaking. And that's it. I'll be working on the concept of slope, because all of these, and here I have a kind of a hint for my next video. So the concept of slope is very interesting, and it is related to Pythagoras. So I will be working on intuitive derivations or fundamentals of some math that I think it's really important when you are learning to code. And yes, so if you follow me till this point, thank you for that, and enjoy these low level coding tricks. See ya.